Hey BC, you've just taken your test and your homework that night is going to be looking at some of these varsity indeterminate forms. I thought we'd go over the strategy for addressing them with a quick screencast, and then you guys should hopefully be able to do some of your homework. We've seen very, very briefly that these varsity indeterminate forms look, there's sort of three flavors. There's 0 to the 0, there's infinity to the 0, and there's 1 to the infinity. Okay, and something you'll quickly notice, right? They all have sort of an exponent, right? And we can't evaluate these guys. I will say there are several other types that are, we can inspect, right? So things we can inspect that don't fall into this category. Can inspect, those would be like, infinity to the infinity, or 0 to the infinity, or infinity to the 1, right? These kinds of things we can inspect, and those don't fall into this category. These guys are sort of murky on the left in black, and we need to think about those. Okay, so an example of one of those would be something like this. We're not going to do this one. We might do this one in class when we come back, but something like this guy. Limit as x approaches 0 from the right, 1 plus x to the 1 over x. We'll talk in class about why we care so much that we're approaching from one specific side, right? Obviously, that exponent might become negative if we weren't, and then we would get something a little bit different. Right, so we care about what side we're approaching from, and given the technique we're going to use, that's particularly important. So, why is this one of those forms? Well, as x approaches 0, 1 plus x, of course, goes to 1, and 1 over x is going to go to infinity, right? So it's that rightmost flavor of 1 to the infinity that we're going to need to address. So the way we're actually going to address these is we're going to think about them as we're going to introduce an extra variable, because we certainly don't have enough. We're going to introduce y, and we're going to set y equal to this sort of exponential thing here with f of x to the g of x, right? Like 1 plus x to the 1 over x. And then, because we really don't like this exponent up here, we're going to we're going to seek to get rid of it. And the way to get rid of an exponent, to have it come down, right, would be to take a log of some sort, right, of log rules, right? So what we're going to end up doing is our technique is sort of going to be to take the limit, the natural log of each side. And when I take the natural log of this side, right, then that g of x can come down, right? Then that g of x can come down, and I'm going to be left with this. And the goal end up with 0 times infinity, okay? And then from there we L'Hopital it. Okay? So once we sort of know what that is, right? Then we can go forward. Okay, so let's talk about these natural logs. Okay, so let's actually do the example we're going to work through today. Now that we've seen sort of the general technique, and then we'll go from there. So let's talk about the limit as x approaches 0 of 1 plus sine x to the 1 over x. 1 plus sine x to the 1 over x. Okay, so if we just inspect this right now, right, 1 plus sine x, sine of 0 is 0. So we're going to get 1, and then, of course, that infinity, from the plus, that 1 over x is going to be positive infinity. So we're going to have 1 to the infinity right now, right? So we say this guy's really 1 to the infinity. And so we have that indeterminate form, right? Okay. Well, let's introduce our y now, okay? So we're going to say, okay, well, we could say y is going to be equal to, not this limit, y is going to be equal to the inside there. Y is going to be equal to 1 plus sine x to the 1 over x. That's nice and happy, right? We're going to sort of ignore our limits for right now, right? And we can throw them in quite soon, though. Okay, and if we think about if this thing is true, well, then this must also be true. If two things are equal, well, then their natural logs are equal. And I know some of you might say, Mr. Perlis, we can't take the natural log of a negative thing. And you're absolutely right. If we look at where this thing is approaching, right, we can sort of guarantee that this thing here is positive, right? If you think about how we're approaching 0, right, let's throw in our limits again. Let's throw in our limits, right? If I have two things are equal, right, then we can take the natural log of both sides and be fine, right? So let's throw in our limits again. And we know, because of where we're looking, that this expression on the right has to be a positive number. So we can take the natural log just fine. Well, the reason we did this natural log thing, right, is again so that g of x would come out, that 1 over x would come out to the front. So that still is this thing, 1 over x times ln 1 plus sine x. Okay, now let's think about what flavor this is. The 1 over x is certainly going towards infinity, right? And the ln of 1 is 0. The ln of 1 is 0, so this is an infinity times 0 thing, and that's sort of what we wanted. And we want to L'Hopital this. Okay, fortunately for us, this one is sort of already in fractional form. And if we L'Hopital it this way, right, this is particularly nice because this x down here is going to go away and become 1 when we take its derivative, right? So we're going to L'Hopital it, and what am I going to get now? I'm going to get 1 over 1 plus sine x in the top times the derivative of sine x, cosine x. We have to chain rule it, all over 1. And that's good. Okay, if we inspect this right now, what do we end up with here? If we inspect this right now, well, that top is just 1 over 1 times 1, right? This thing is just, in fact, equal to 1, right? We can just inspect this right now. Inspect it. I forgot, by the way, this should say, 0 over 0. And we're thinking about what that is. Okay. So we inspect this thing, right? And we just get this thing equals 1. But what was this thing? Our answer is not 1. I put that in a box, and actually I probably shouldn't have, right? Let's erase it. I put that in a box. Probably shouldn't have. This was the limit as x approaches 0 from the positive side of ln y. Well, there is no x on that side, right? There's no x over here, so I can sort of ignore that limit. So we're saying the natural log of y is 1. And if we say where is, and we can do this, right? There's no x. We can sort of ignore that limit. The natural log of y equals 1. Where is that true? Well, of course, then y has to be e. Y has to be e. That is my actual answer, right? This limit y equals e when x gets close to 0. Okay, and if we go to Desmos, we can see that we've graphed this thing. First of all, that function looks really, really weird. Look at this behavior. It's kind of strange. But if we zoom in at 0 and sort of move our mouse along, right? So it's obviously undefined, but we can verify, right? This is e in there, right? These numbers are very, very close to e. So that is that thing's limit as we get close to 0. Obviously, we can't actually inspect it there because it's not defined. So we get y equals e. Okay, so we've shown that as the natural log of 1, the natural log of y gets close to 1 as x gets close to 0, right? Therefore y must get close to e as x gets close to 0, right? So let's write that. Because ln y approaches 1 as x goes to 0, y must approach e as x gets close to 0. And what was y? Y was 1 plus sine x to the 1 over x, right? So therefore 1 plus sine x to the 1 over x approaches e as x gets close to 0, right? That's sort of the logic that we use here, right? Natural log of y approaches 1 as x gets close to 0. Y has to approach e as x gets close to 0. So therefore, all of these are 0 plus. All these are 0 plus. So I think you'll be able to address your homework if you try it this way. This was a relatively easy example. We only had to use LHOP once. But I think you should be able to get started on some homework exercises tonight. Good luck on those. We will practice plenty tomorrow.